This is a lesson on Pascal's principle in fluid statics and dynamics. Now that we're getting an idea of how forces interact with fluids and how to quantify pressure with a fluid, we can look at Pascal's principle, which is an application of it. What Pascal's principle says is a change in pressure applied to an enclosed fluid is transmitted uniformly to all portions of the fluid and its container walls. And so I have a diagram here. You can see that it's a simple model of a hydraulic system. There's a force applied on one side, and this will be the smaller side. What happens is the fluid moves through the system to the larger reservoir, and that reservoir is able to apply a force. And that force applied on the first area gets transmitted to the second area. Well, because they are at the same height, and this has to be true, they have the same amount of pressure above them, they have the same amount of pressure below them, they're both at the same pressure. So that's why I wrote here P1 of some height has to equal P2 of some height. So the pressure here has to equal the pressure here. Okay, and you can see that in the diagram. Well, we know the equation for pressure, force over area, so we can say that force 1 over area 1 equals force 2 over area 2, and that's the essential Pascal's principle. This is the hydraulic chamber. A hydraulic chamber with a spring attached to the input piston. So you can see over here, here's the spring, and this is the input piston. So this is the P1 side. And a rock of mass 50 kilograms on the output piston. So over here is the rock of a mass 50 kilograms, and this will be the P2 side. And I'll make note that M equals 50 kilograms. The pistons are at the same height, and each has negligible mass. How much force is the spring applying to the input piston? So this is a static situation. So what I know due to Pascal's principle is that P1 has to equal to P2. And I can say that F1 over A1 equals F2 over A2. When I think about F1 will be the F of that spring there, right? The spring is pushing down, F spring, and it is the fluid transmits the force of that spring over here. It balances out because there's no motion. It balances out the weight, the force of gravity on this mass. So over here, F2 will equal the force of gravity on the mass, which is mg. It wants how much force is the spring applying. So I'm going to solve for F1. So the spring force has to equal F2, which is mg, times A1 over A2, right? I multiply by A1 on both sides and I get A1 over A2. And I like doing it this way because then I get a proportion of the areas, and it doesn't matter what units the areas are in. You can notice over in the diagram that the two areas are in centimeters squared. You may be inclined to convert those units to SI, which you could do and not be wrong in doing. But because I have a proportion here, I'm not going to worry about converting them because the units and any conversions would cancel anyway. So let's put in the numbers of what we know. 50, a factor of gravity, 9.8. A1 is 15. And A2 is 65. And what I'm going to note is that the force being applied by the spring is less than the force being applied by gravity, right? It's a factor of 1 multiplied by that force. So it's going to be less than the weight of the force. And that's the idea of hydraulics, right? You shouldn't have to push as hard on one side in order to get work out on the other. So there will be a difference in these forces, and the one where the area is smaller is going to have a smaller force. When you solve for the force of the spring, you get 113 newtons. So that isn't a very large force at all. The next problem I chose is the U-tube problem. And you can see that there's a tube shaped like a U, and in it is two fluids, this red fluid and this green fluid. The red they're calling 1, and the green they're calling 2. There's an H1 and an H2 and a density 1 and a density 2. two liquids, 1 and 2, are in equilibrium, so a static situation, in a U-tube that is open at both ends. When it's open at both ends, what we're going to assume is that there's the atmospheric pressure on both sides on top here, such that P1 on the top is equal on both sides. You may be getting the feel here that we're going to be dealing with pressure. There's a P2 level down here, P2 on this side and a P2 on this side. And so that it's the same across here. And that's what Archimedes' principle basically says, right? At some height, the pressure on the left side at this height has to equal the pressure on the right side. And that's on the top or on the bottom here. So this pressure at the bottom, P2 down here, has to equal the P2 down at the bottom here. So that's just thinking about pressure as we're getting into the problem. It says the liquids do not mix, so maybe oil and water sort of situation, and liquid 1 rests on top of liquid 2. It is known that the density of liquid 2 is 1025 kilograms per meter cubed. This looks like salt water. Okay, so we have some salt water here, and then we have some liquid sitting on top. The first question asks, and there's some options here, how does the density of liquid 1 relate to the density of liquid 2? Okay, so we know liquid 2, and the only difference here, it seems like it's the same area, so I'm not going to worry about area. When you think about pressure, area is involved, so that's not a consideration. The only difference other than the densities is the two heights here. So I can see in this situation that the height 1 is less than the height 2 on the left side as opposed to the right side. Okay, so I don't need as much of the first liquid in order to cause the same amount of pressure on the other side with the other liquid. And I know that pressure is related to height and density, right? Pressure is, when I think about it, rho GH under a liquid or any sort of substance, rho GH. If I have a density and gravity and a height, that gives me some additional pressure. So when I was talking earlier, the pressure on the left side has to equal the pressure on the right side. Well, let's set this up. We have 1 atmosphere at the top, right? The pressure of an atmosphere plus rho 1 GH1 over on the left side has to equal the pressure of 1 atmosphere plus rho 2 GH2 over on the right side. And just like we expected, this 1 atmosphere is the same on both of these, and so we're really just worried about the pressure, the additional pressure due to the two liquids. So let's write this out. Rho 1, and I'm going to cancel a factor of g in both of these terms as well, so I'm not worrying about that factor of g unnecessarily. So rho 1 H1 equals rho 2 H2. Let's solve for rho 1. It's unknown. Rho 1 equals rho 2 times the ratio of H2 over H1. Okay, so when I look at this, is that H2 is greater than H1, so this factor here is greater than 1, and so I'm going to get rho 1 is greater than rho 2. Because I'm multiplying by a factor greater than 1, I'm going to get something greater than rho 2 over here, and so this will be my answer. Does this make sense? Does this make sense? When I look at this, I can see that it doesn't take as much volume of liquid in order to create the same amount of force on this side as it does on the right side. So there must be a larger density over on the left side in order to cause it to need less material to be the same weight as over on the right side. So that's the answer to part A. Let's do part B. It says, what is the density of liquid 1 if the heights of the liquids are 5.6 and 8.2? So H1 equals 5.6 centimeters, and I can see it's smaller, so that makes sense to me. H2 equals 8.2 centimeters. I already have an equation up here. Rho 1 equals rho 2, which I know is 1025. And then I'm going to multiply by a factor of 8.2 over 5.6. When I run this through my calculator, I get 1,501 kilograms per meter cubed, and I expected something larger than 1025. And so that makes sense to me.